During World War II, the Boeing B-17 Flying Fortress was one of the most important aircraft in the American arsenal. It flew long missions deep into German territory, carried heavy bomb loads, and was advertised as one of the most durable airframes ever built. Photographs circulated of B-17s returning with massive holes in their wings or tails, yet still landing safely. These images shaped the bomber's reputation as a machine that could take punishment and keep flying. But by late 1943, the reality behind the statistics was far more complex. The B-17 was rugged, but the air war was evolving faster than the engineers who designed it ever anticipated. German defenses grew stronger, flak became more accurate, fighters struck from new angles, the aircraft was pushed into environments Boeing never fully tested for. Crews flying these missions began to notice something the promotional material didn't admit. Many B-17s weren't being lost because they were destroyed outright. Instead, they were lost because a single hit often caused failures in systems that were never designed to withstand real combat damage. Losses continued to rise. In the fall of 1943, the 8th Air Force was losing roughly 5% of its bombers on each mission. A crew needed to complete 25 missions to finish a tour. Statistically, that gave each crew nearly even odds of surviving the war. Every man who stepped onto a B-17 understood the math. They knew that one fragment of flak hitting the wrong line or cable could bring down a 4-engine bomber. This vulnerability was not widely discussed. Official reports tended to attribute losses to intense flak or enemy fighter pressure. But on the maintenance lines, where bombers returned battered and broken, certain patterns became clear. Critical systems were placed in predictable areas, routed through narrow access points, or bundled together to make manufacturing easier. Efficient design in Seattle did not necessarily equal survivability over Germany. The growing problem remained unaddressed until the work of one mechanic changed everything. Staff Sergeant Paul Zuck did not come from the background most military aviation experts came from. He wasn't a trained engineer. He had not attended Army technical school. He understood machinery because he had lived around it his entire life. Before the war, Zuck ran a repair garage in Pittsburgh. His customers included coal haulers, delivery drivers, and anyone who needed their truck or car repaired cheaply and quickly. He learned how to stretch parts, salvage materials, and rethink systems when money or equipment wasn't available. His work was guided by a simple rule: if something didn't work, find a way to make it work anyway. When the Army Air Forces assigned him to the motor pool in 1943, it assumed he would be working on jeeps and trucks. But someone saw a note in his file about his civilian mechanical experience and transferred him to aircraft maintenance at RAF Bassingbourn, home of the 91st Bomb Group. The decision appeared trivial at the time. In reality, it would quietly reshape bomber survivability for the rest of the war. Zuck's introduction to B-17 maintenance was quick and revealing. He watched how different crews approached repairs. Many mechanics were highly skilled and knowledgeable, but they followed the technical manuals exactly. If a line was cracked, they replaced it. If the part wasn't available, the aircraft stayed grounded. The manual dictated the process, and deviating from it was discouraged. Deviations required authorization, paperwork, signatures, and approvals that rarely came through quickly. War rarely respected these time constraints. One of the first things Zuck noticed was a B-17 being held from a mission because of a hydraulic line defect. The damaged section could have been bypassed, but the manual didn't allow that. Regulations required the entire line to be replaced. Replacement parts were back-ordered. As a result, the bomber didn't fly. Zuck asked a simple question: why can't we reroute it temporarily? The answer was equally simple: because the manual doesn't say we can. Zuck realized immediately that the manuals were written for ideal conditions, not for a high-loss environment where damage was inevitable. Combat did not care about authorized procedures. B-17s were being shot down because they were too dependent on single systems with no backup pathways. A single hit to a hydraulic line could disable landing gear, flaps, and brakes. A punctured fuel line could cut off the flow to multiple tanks. An electrical hit could shut down turrets or instruments. While the official stance was that the B-17 could survive extreme damage, Zuck saw that only certain types of damage were survivable. Others were fatal not because the airframe failed, but because the internal systems were vulnerable. He had seen the same pattern in civilian vehicles. A truck wasn't useless because a fuel line cracked. It only became useless when the system had no alternate routing. So Zuck began quietly modifying aircraft in ways that made sense based on his mechanical instincts, not based on what the manuals allowed. He didn't announce what he was doing. He didn't write it on official maintenance forms. Instead, he worked during night shifts when fewer officers were present. His first focus was the hydraulic system. The B-17 had a clean, centralized hydraulic line system designed to simplify production. The main line ran through predictable sections of the fuselage. Zuck saw that a single hit in that area almost always caused complete hydraulic failure. He began creating backup lines. Using salvaged tubing from damaged aircraft, he added secondary routes, installed manually operated valves, and placed them within reach of the pilots. If the main hydraulic line was damaged, a pilot could switch to the backup line instantly. Next, he addressed the fuel system. German fighters often attacked from the side, precisely where the fuel lines passed between tanks. If a single line was hit, air entered the system and engines began failing in sequence. Zuck installed crossover valves and additional isolation points. If a line was hit, the crew could isolate the damaged tank and reroute fuel from undamaged ones. His third major modification involved the electrical system. The B-17 relied heavily on a centralized power bus. If the wrong section was damaged, radios, instruments, and gun turrets could fail simultaneously. Zuck installed alternate pathways from the auxiliary generator directly to critical systems. These emergency circuits were manually controlled and bypassed the main electrical bundles entirely. None of these modifications followed official procedures, yet every single one was logical and grounded in real-world damage patterns. Zuck knew exactly why these changes mattered, because combat rarely damaged aircraft in predictable or manageable ways. He documented everything in a personal notebook: sketches, system diagrams, pressure readings, and safety notes. Nothing appeared in formal maintenance logs. By late 1943, something unusual was happening. The bombers Zuck worked on were coming home from missions at noticeably higher rates. Several aircraft returned with damage that should have made landing impossible. One bomber landed with complete primary hydraulic failure, yet its wheels extended using Zuck's backup lines. Another plane kept its instruments powered despite electrical damage that should have shut everything down. To the crews, this seemed like extraordinary luck. To Zuck, it was the predictable outcome of adding redundancy. The turning point came when an inspection officer discovered Zuck's modifications. Captain Ronald Fletcher, an engineering supervisor, opened an access panel on a B-17 and found hydraulic routing that wasn't in any Boeing blueprint. He confronted Zuck, discovered that 17 bombers had already been modified, and reported the situation to Group Commander Colonel James Albertson. Normally, this would have resulted in immediate disciplinary action. Unauthorized modifications to combat aircraft were a serious offense. But Albertson had already witnessed one of Zuck's modified planes returning from a mission in a condition that should have been fatal. He remembered the landing of the B, Lucky Strike, which survived failures that defied official expectations. So instead of punishing Zuck, the Air Force conducted an investigation. Major Henry Watkins from 8th Air Force Engineering, accompanied by Boeing representatives, arrived to examine the modifications. At first, the engineers reacted negatively. The designs broke standard principles of system routing and violated multiple regulations. They believed the changes introduced new risks. But when they saw how Zuck's planes performed under combat conditions, their perspective shifted. The data from missions involving modified aircraft showed significantly higher survivability, especially for planes hit in critical system areas. Watkins recommended formal testing under real combat conditions. 5 modified B-17s were equipped with additional monitoring instruments, pressure gauges, fuel flow sensors, and electrical load recorders. These aircraft flew 11 missions in March 1944, 3 sustained heavy damage, all returned. Data showed that the backup hydraulic, fuel and electrical systems worked exactly as intended. The results were undeniable. Zuck's unofficial fixes directly addressed design vulnerabilities the official engineering teams had never corrected. The Air Force had a decision to make: punish the sergeant who broke regulations or adopt his methods. They chose the latter. A technical order was drafted to authorize hydraulic modifications. Mechanics across East Anglia began learning the method. Unofficially, many also copied Zuck's fuel and electrical improvements before formal approval arrived. By June 1944, more than 100 aircraft across multiple bomb groups had been modified based on Zuck's work. Survival rates increased. Abort rates due to mechanical failure dropped. Statistical analyses showed a clear link between modified aircraft and mission success. This shift didn't come from laboratories or design offices. It came from one mechanic who understood practical engineering better than the rulebook. And in the second half of the war, the full impact of these changes became impossible to ignore. As the authorized modifications began rolling out across the 8th Air Force, the atmosphere on the flight lines started to shift. Mechanics talked to each other during supply runs at mess halls and while waiting for parts shipments, and one thing spread faster than any official directive: Zuck's methods worked. Word of mouth became the real distribution system. Crew chiefs from nearby groups visited Bassingbourn to see the modified hydraulic systems for themselves. Others copied the ideas after hearing from pilots who returned from missions because a backup line saved their aircraft. In an environment where survival statistics shaped morale and mission planning, even cautious officers began paying attention. Mechanics were not motivated by bureaucratic procedure. They were motivated by watching crews return alive. This mindset drove adoption faster than policy ever could. By mid-April 1944, at bases like Molesworth, Thurley, Thorpe Abbotts and Kimbolton, nighttime maintenance shifts included unofficial training sessions. Mechanics gathered around open access panels while someone who had learned the method explained the routing pattern. Even those who had never met Zuck personally repeated his logic. If the enemy can break the primary system, then we need a secondary one that doesn't run through the same place. This wasn't rebellion, it was adaptation. The war was forcing the aircraft to evolve faster than official channels allowed. The formal technical order eventually authorized only the hydraulic modifications because they were the easiest to document and the least controversial. But unofficial work continued behind the scenes on fuel and electrical systems. These changes were simple enough to implement without specialized tools, yet powerful enough to prevent fatal cascading failures. When combined, the 3 improvements turned a B-17 from an aircraft that could survive visible structural damage into one that could survive invisible internal damage as well. By May 1944, statistical patterns began emerging. Groups that had implemented Zuck's full suite of unofficial and official changes saw fewer aborts and more aircraft returning after sustaining hits that previously would have been mission-ending. One surprising effect of the modifications was how pilots adapted to them. During briefings, navigators and co-pilots were shown the placement of new manual valves. Pilots were told that backup lines existed and how to activate them. The presence of these alternatives changed how crews responded to damage in the air. They no longer assumed that losing hydraulic pressure meant an unavoidable belly landing. They no longer believed a rough engine automatically meant fuel system collapse. Their confidence improved, not recklessly but pragmatically. This improvement in confidence mattered. A crew that believed it had options was more likely to stay with the formation, complete the bomb run, and make it back across the English Channel. By June, group commanders compared maintenance reports and mission outcomes. The 381st Bomb Group at Ridgewell saw a notable drop in mechanical losses. The 100th Bomb Group, nicknamed the Bloody 100th for its heavy losses, saw a measurable improvement in return rates after mechanics adopted the unofficial fuel and electrical upgrades. These weren't classroom theories, they were field-proven changes executed under combat pressure. The Air Force's engineering branch eventually received an internal statistical summary that highlighted the trend. Planes with redundant hydraulic routing were significantly less likely to be lost after a flak burst hit the lower fuselage. Those with fuel crossover valves were far less likely to suffer cascading engine failures, and aircraft with redundant electrical paths retained functional turrets more often, allowing them to protect themselves during withdrawal. Behind these numbers was a simple truth. Redundancy didn't make the aircraft invincible, but it turned avoidable losses into recoverable situations. As the Allies prepared for major operations following D-Day, bomber missions intensified. Zuck's modifications were now spread across more than a dozen groups. Even as the air war moved deeper into Germany, many of his concepts became standard practice in field maintenance, with or without official approval. The changes didn't transform the B-17 into a new aircraft, but they made it far more robust. Mechanics noticed something else as well. Modified planes were easier to repair after missions. Because backup systems were installed, crews could return to base with partial failures rather than total ones. This gave maintenance teams additional time to perform thorough repairs instead of rushing to fix catastrophic failures before the next mission cycle. The B-17, already known for its durability, became even more capable of enduring the worsening conditions of late-war air combat. By early 1945, when the air war reached its final phase, the impact of Zuck's work had fully matured. More aircraft survived heavy flak corridors, fewer planes crashed in the North Sea due to system failures, and more crews returned home to complete their tour. Statisticians at the 8th Air Force compiled these trends during the spring of 1945. The conclusions were clear. Aircraft modified with Zuck's methods had significantly higher return rates under identical combat conditions. The numbers told a story the official manuals never anticipated. After the war, a deeper analysis provided an even more striking picture. When the Air Force evaluated wartime loss reports, maintenance logs, and pilot testimonies, one figure stood out. Planes equipped with full redundant systems, official and unofficial, returned at almost twice the rate of unmodified counterparts when sustaining similar damage classifications. The data was so strong that post-war design teams quietly incorporated lessons learned from these field modifications into new bomber designs. The B-29, B-50, and early Cold War aircraft began using more distributed system layouts, greater redundancy, and more isolated routing to prevent single-point failures. These changes were not directly credited to Zuck, but the engineering shifts mirrored his concepts. In military terms, the service rarely acknowledged individual mechanics who solved systemic problems. But in practice, the principles he introduced became part of how modern aircraft were built. As for Zuck himself, he never sought recognition. He left the Army Air Forces at the end of 1945 and returned to Pittsburgh. He went back to running his repair shop. To neighbors and customers, he was simply a skilled mechanic who could fix almost anything. Few knew he had influenced wartime aviation in a significant way. The logs he kept during the war, his sketches, notes, and explanations, eventually became part of an archive, but his name never became widely known outside of technical history circles. In later interviews, he explained his motivation plainly. When asked why he risked violating regulations, he said he didn't view it as taking a risk. He viewed it as preventing unnecessary deaths. The regulations, he believed, were written for situations far removed from the reality of combat. There was no sense of rebellion in his work. It was simply the application of practical engineering under extreme conditions. He cared about the crews who flew the aircraft, and he cared about giving them the best possible chance to survive. Today, Zuck's story illustrates something enduring about wartime innovation. Important advancements don't always originate from high-level design teams or official programs. Sometimes they come from individuals on the margins, people who see problems firsthand and use their expertise to find solutions quickly, people who understand that systems must adapt to reality, not the other way around. The success of the B-17 Flying Fortress in the final years of the war was a team effort involving pilots, gunners, mechanics, engineers, and commanders. But Zuck's contributions helped close critical gaps that had cost lives earlier in the conflict. His modifications turned theoretical survivability into practical survivability. These changes didn't appear in wartime newsreels. They weren't part of speeches or reports. They happened in hangars under harsh lights late at night with limited parts and limited time. Yet they made a measurable difference where it mattered most, in the number of crews who completed their missions and returned home. As historians continue to analyze the air war over Europe, stories like Zuck's show how complex that victory truly was. It wasn't just strategy or technology. It was also initiative, observation, and the willingness of individuals to improve systems even when they lacked formal authority to do so. What began as a mechanic's quiet effort to solve a recurring problem became one of the most impactful field modifications in the history of the 8th Air Force. And while his contributions were not widely recognized at the time, his work influenced the way future aircraft were built and maintained. The lesson Zuck left behind is straightforward. Systems fail, but good engineering anticipates failure. Redundancy saves lives, and sometimes one person paying close attention can change the outcome of an entire conflict.